And we're live. Okay. Happy holidays, everybody. Hope everyone's enjoying some time off, ideally. I've taken some time off over the last couple days, but am getting back on the advent of code horse, so to speak. And last time we finished up part A of day 13, which wasn't too bad. We just had to parse out how basically to compare these two sets of lists. They gave us some rules as to how to compare them. Cool stuff. So we got to part 2 and read through it, but I'll go through it again now. I don't remember all the details, and I would rather not miss some detail. Those are often the trickiest bugs to find, because like all your tests are passing, but you're failing the actual submission, and it's because you didn't read the question. So part 2, now you just need to put all of your packets in the right order. Disregard the blank lines of your list of received packets. The distress signal protocol also requires that you include 2 additional divider packets, bracket bracket 2 bracket bracket and bracket bracket 6 bracket bracket. So the list containing the list of 2 and the list containing the list of 6. Using the same rules as before, organize all packets, the ones in your list of received packets, as well as the 2 divider packets, into the correct order. For example, this. Afterwards, locate the divider packets. To find the decoder key for this distress signal, you need to determine the indices of the 2 divider packets and multiply them together. And they are 1 indexed, which is really easy to forget. So in this example, they are the 10th and 14th, so the decoder key is 140. Organize all the packets into the correct order. What is the decoder key for the distress signal? Sweet. Okay, so what's our approach going to be? Well, broadly, we insert packets. There are presumably going to be a fair number of them. If we look at the input 13, there are 449 lines, roughly a third of which are, so 450 basically, roughly a third of which are blank, so there's like 300 things to sort. Not too bad. Shouldn't be too bad. I guess 302 things to sort if you're gonna stick the 2 new placement packets or divider packets or whatever they're called in there. And then we need to dig out where those 2 packets wind up. And so the sorting algorithm that I learned at one point that I've not looked at in a while, I can't remember if it's called like swap sort or might be quick sort. Sounds familiar? I think it might be quick sort. It's super common. It's like CS 101 type thing. I just never took real algorithms classes. So I have a math background, not a computer science background. So my knowledge of these is all kind of self-taught, self-learned over time as things have come up that have been relevant. But I have done it before, and hopefully I will be able to work out how to do it again. If I can't, I will look it up. But I think I remember the basic idea. So before we get to the actual sorting algorithm, let's go ahead and set up the tests. So we have problem 13b, it passes. Let's grab example input just like we did last time. And this time we will use 13b. And the example answer was 140. And that'll make sure that we're sort of an integration test, make sure that we're actually solving the question. And then this guy will try to solve problem 13b, and we'll see what happens there. That's fine. And so obviously we're going to want a test that tests the sorting. I'm trying to think if there's any other tests that we want. I guess there's going to be the question at the end of this, how we find the two packets that we put in there. Because I think for the most part, sorting algorithms don't really keep track of the index of any of the items. So obviously we can just scan the resulting thing, and I mean it's only going to be 300 long, so that's probably the easiest thing to do is just scan it. Should be fast enough. So yeah, so I guess really the next and only test I think we'll need is sorts correctly. And for this, what to do? So let's get the example input again, and let's parse out the, so we're not going to parse it into pairs anymore. We are going to strip out the white space and just parse each one individually. So for that, I don't know, do we need packet part? Yeah, I guess let's use a function in packet part for that. So we'll say let unsorted, or let packets be packet part parse. Let's see here, we had from string. So if we do from strings, and then example input into iter filter x dot length is greater than 0, select it. That can be our parser. And then this should be mutable probably. So that'll be a list of packets, and then we'll just say packet part sort packets. And we can just sort it in place. And then we'll say let expected should be a vector for sure, and the vector should have what? Let me grab it from here. Except it will not have it's a 2. Okay. It will not have this or this in it because those are the special those are the special ones that you add. And we'll say toString. And then we'll just parse this. So we just get to say assert equal packets and packet part from strings expected. Okay. Cool. That should work pretty well, I think. Let's go up here and just this is essentially the implementation of the is essentially what we want in our actual function that solves the puzzle. So let's just call this, we don't need that at all. It's a vector of strings. We take example input and filter it down, sort it, except that we need to add our 2 packets to it. So we say packets.push, packet part from string. So it's this one, and it's 6, right? 2 and 6. And there are like real questions here of like, where should I be putting these to start with? Like with any of these sorting algorithms, it ends up mattering, I think, quite a bit. At least my intuition is that it matters quite a bit, that the, like, exactly how you pick sort of initial conditions will affect the performance of the algorithm. I'm just kind of skeptical that with 300 things, the performance of the algorithm is going to be that important. So, like, honestly, there's another way to do this that doesn't involve us writing our own sorting algorithm at all, where we could just implement the compare, like CMP is a trait that you can implement on a type, so we could implement it on packet part, and then we could just call the sort operation rather than implementing it ourselves. Which, now that I'm saying it, like, I don't know why I wouldn't just do that. It's certainly more rusty. It's like somewhat less fun. Yeah, I guess I'm just gonna do that now that I think about it. So this will actually be packets.sort, and then let idx2 be packets.find. Let's call this packet 2. And we'll just do the same thing for packet 6. This will just become packet 6, and then find packet 2, expect, is find correct? Okay, it doesn't know what type packet part is, so it can't tell me, that's fine. And then let idx6 is packets.find packet 6. I mean, none of this is going to be the most efficient thing in the world, right? Like, we could binary search this in a way that, you know, maybe we're repeating work basically between these two things, but again, I don't think it's going to be that important for sorting 300 items. Packet 2, packet 6, and now we want to return idx2 plus 1 because it's 0 indexed, or it's 1 indexed, idx6 plus 1. Return that product. Okay. These both need to be toString. And let's actually go back to our test and update this. This is just going to be packets. Sort. Okay. From strings should be very easy to implement. So let's do that first. It's technically, it should be up here. Pub function from strings takes a vec of strings. And returns a vec of self, and is just literally strings into iter map from string s, and we collect. And then packets.find packets.sort. So sort doesn't work yet because, oh, it's not CMP, it's ORD. But okay, I mean, basically we just need to implement the trait ORD for packet part. So let's do that. Impl ORD for packet part. And I'm going to need to remember I'm not going to remember it, I'm just going to look it up. Rust impl ORD. It's derivable, but I don't want it to be derivable. I want it to be let's get rid of this, get rid of this, get rid of this, and then this will be for packet part. And this will be match let's see here, self dot compare. What did I do last time? Self is ordered. Self other. Then if it's true, we say ordering less than. Ordering less. False. Ordering greater. This is some true, some false. You know what though? Actually, we did this even better because partial ordering. Partial ordering wants exactly what we already have. So here we just say, not exactly, but here we say this. Some true, some ordering less, some ordering greater, none. I mean, it's really ordering equal. Is it EQ? No, it's equal. And then this one just becomes match self dot partial CMP other, and if it's some S, we return, well, we basically just unwrap, actually. Expect partial CMP doesn't return none. And let's get rid of all this. And import ordering. Okay. And wrap this in some. Cool. So partial ordering, if people don't know, partial orderings, two things mean that you can always say that whether something is less than, greater than, equal to, or not comparable at all. So something like, I can't think of a good example of something that's not comparable at all at the moment. Maybe like subset. You can have equal sets. You can have one set be a subset of another. One set can be a superset of another. Or they can be neither. That would be a partial ordering. And then an actual ordering is, there's no none there. So instead of returning an option ordering, it just returns an ordering. And the idea is that our sort algorithm needs to know how to sort, needs to know how to order. Apparently it uses timsort. Okay. In order to do that, it needs T to be ORD, so we've just implemented that. Okay, and then find is apparently not a thing. Is it index? Performs the indexing? No. It's not get. Search. Binary search. Sure. It's ordered, so we can use binary search packet 2. Binary search packet 2 has to be a reference. And now we want to expect packet 2 should definitely be in the packets. And we can just do the same thing here. Okay. And we're trying to borrow these, which we don't want to do, so let's clone them here. Okay. So everything compiles. This is going to sort them, I believe, in the correct order. Should sort them ascending, which is what we would say this is. So I'm cautiously optimistic. One failed. It is our test. It passed the example, and it's hitting the blank, basically. And so I kind of expect this to just be the answer. And we didn't have to implement our own sorting algorithm at all. 21276. Let's see if we did it. Let's see if I can find what happened to my advent of code. Oh. 21276. We submit. It's the right answer. We are one gold star closer to collecting enough starfruit. All right, we've completed day 13. We are more than halfway through the advent calendar. This is exciting stuff. As you can tell from the thrilled way that I just said that. No, it is exciting stuff. I'm drinking tea today instead of coffee, and it's, I don't know. It's putting me in a calm space. Okay. Day 14, regolith reservoir. I don't know what a regolith is. Lith means stone in Greek. Is this an actual thing? A region of loose, unconsolidated rock and dust that sits atop bedrock. Fascinating. Okay. The distress signal leads you to a giant waterfall. Actually, hang on. The signal seems like it's coming from the waterfall itself, and that doesn't make any sense. However, you do notice a little path that leads behind the waterfall. Correction, the distress signal leads you behind the giant waterfall. There seems to be a large cave system here, and the signal definitely leads further inside. As you begin to make your way deeper underground, you feel the ground rumble for a moment. Sand begins pouring into the cave. If you don't quickly figure out where the sand is going, you could become trapped. Fortunately, your familiarity with analyzing the path of falling material will come in handy here. You scan a two-dimensional vertical slice of the cave above you, your puzzle input, and discover that it's mostly air with structures made of rock. You scan traces of the path of each solid rock structure and reports the XY coordinates that form the shape of the path, where X represents the distance to the right and Y represents the distance down. Okay. Each path appears as a single line of text in your scan. After the first point of each path, each point indicates the end of a straight, horizontal, or vertical line to be drawn from the previous point. Scan needs that there are two paths of rock. The first path consists of two straight lines, and the second path consists of three straight lines. Specifically, the first path consists of a line of rock from there to there, another one, okay. Each path appears as a single line of text on your screen. Scan trace of the path of each solid rock structure and reports the coordinates that form the shape of the path. Okay, so these are the edges of rock. Okay. The sand is pouring into the cave from point 500, 0. Is it up or down? Drawing rock as £, and air as this, the source of sand as this. Okay. This becomes, okay, so 0 is the top, source of sand, and here's some rock. Okay. Sand is produced 1 unit at a time, and the next unit of sand is not produced until the previous unit of sand comes to rest. A unit of sand is large enough to fill 1 tile of air in your scan. A unit of sand always falls down 1 step if possible. If the tile is immediately below is blocked by rock or by sand, it attempts to move diagonally 1 step down to the left. If that tile is blocked, it attempts to move diagonally 1 step down to the right. Sand keeps moving as long as it's able to do so, at each step trying to move down, then left, then down right. If all 3 possible destinations are blocked, it comes to rest and no longer moves, at which point the next unit of sand is created at the source. So drawing sand that has come to rest is 0. First unit of sand falls straight down. Second unit falls straight down, lands on the first one, comes to okay. Sure. Yep. Once all 24 units of sand shown above have come to rest, all further sand flows out the bottom, falling into the endless void. Just for fun, the path any new sand takes before falling forever is shown here. Using your scan, simulate the falling sand. How many units of sand come to rest before the sand starts flowing into the abyss below? To begin, get your puzzle input. All right. This is all very exciting. Let's create input 13. 14. Is our puzzle input. And in problem 14, let's get rid of this. What's the sample input like? Yeah, the sample input is really short, right? Yeah, the sample input's really short. Okay, so we'll do an example function here, get example input. It will return a vec of strings, and it will be just this. Oops. Okay, so that will be our example input, and then we can say assert equal solve problem 14a of get example input, and the answer should be, what was it, like 22 or something? 24. 24 will be the answer. Okay. Cool. So that gives us our integration test, so to speak, and we need to figure out how to solve this thing. So, I mean, basically, the answer here is just going to be to simulate exactly what happens. I don't think there are any tremendous shortcuts. So it's a modeling question, essentially. I'm throwing T all over the place. So what to say? We've got a two-dimensional grid. We're going to need a way to query that grid to be able to populate additional steps or additional sand spots. I don't know what to call them. So it's going to be something like, let's just write a test, simulates a drop, simulates sand drops. And we'll say let mute cave be cave new maybe cave from strings, get example input, and then we'll say cave dot simulate, or let's say drop sand. Let's assert that it's not the case that what should we say? Abyss cave dot, what do they say? Endless void blah blah blah. Is sand in abyss. Let's assert that so there's an organizational question here. I guess we're going to want the internals to be a hash map from a certain location to whether or not it has sand in it, because that's mostly what we want to look up, right? We want to, for a given drop of sand, we're going to want to say, like, is there something below it? Is there something to the bottom left and bottom right of it? So let's say cave.get, and where's it gonna land? It's gonna fall straight down. This is 500 0 for some reason. So it's gonna fall straight down. 500, 1, 2, 3, 4, 5, 6, 7, 8. So 508. Let's also say back to new 500 0. Back to new 508. So we will get that. I think that can be a reference. Not that it really matters. It's a value type, it's fine. And then that should be true. And let's just why don't we like this? End of macro invocation. Why? Okay, it's not. 500. Ooh, it's actually not. It shouldn't be true though. It should probably be something like material sand. And then we'll do material rock, because this is right below. And to either side, let's do 508, 499, and 501 is what we want. So 499, this should be 8, and this should be 501, and these will be air. Yeah. Okay, so basically the cave will let us query for what kind of material is at a certain point. So then let's drop sand again. I guess instead of saying where the sand is coming from every time, this is not going to matter. This is just an API design choice, but we can do it here. So let's say let sand entry location be 500 0. And I think this is copy anyway, so it should be fine. So we can just drop sand here. And now it's going to be more or less the same thing, but slightly different. There's still going to be no sand in the abyss. There will be sand at 508 because that's the first drop of sand. There will be sand at. There will be rock below it. There will be sand to the left of it, though, because now the sand can go to its angle of repose or something. Okay. I guess we may as well keep going here and say let's just say cave.drop sand until abyss sand entry location. And now we will do sand in abyss. And let's assert that cave get non-abyss sand is 24. Okay. And I think this should be pretty good. Pretty comprehensive test. Let's import vec. We're gonna implement material. We're gonna implement cave. And yeah, this should be pretty straightforward from here. In fact, we can start with the outermost function. Which is basically going to be something like this. So it'd be from strings, input, sand entry location is good. We won't do any of this. We will just do this. And we don't need to assert anything, and we will just return this. Should be fine. Okay, and we're unhappy here because we needed to import outside. I understand why when you auto import in VS Code, it puts it inside your, from within a test, it puts you inside the test module, but because I write tests first a lot of the time, I often end up doing my auto importing from there. It's not my favorite. Okay, let's implement some stuff. So the easiest thing is probably material, which can be all of the things. It could even be more than this, but this should be plenty. Oops. Material can be air, rock, or sand. Don't think there's too much to that. And then for cave, certainly can't be copy. I guess it can be clone. I don't have a problem with that. Don't think it should have default. I mean, equal, partial, equal, sure. Construct cave. And this is going to be a hash map of vec2 to material. Call it map. And we will import. Okay. And so, import cave, function new, map, hash map, vec2 material, self, and just return the self map. And then from strings is going to be the more common thing. That will take a vec of string. It will return a self. And what to say here? I mean, it's basically like strings dot into iter dot map will have some self two points or lines. You say line 2 point. let's say lines 2 points. Yeah, let's start here, and then we'll map 2 lines 2 points. That'll be a bunch of points, and then for each point we will say P material rock dot collect and this now is, let's see here, this is the map, so we'll say let map equal this, and then we'll say self new map. Function lines 2 points. We'll take a vector of strings. No, we'll just take a string. Maybe it's just string to points. We'll say lines. String, it will return a vec of vec2s. And we will say let endpoints be lines.split on, it's this. Yes. And then we'll say dot map endpoint. I guess we have to say s. S dot split on a comma. And let's do these a little bit better. So split, split. And then this is going to be chords. And we'll say, let's do this one in a block. And then at the end of it, we'll just collect. And those are all the endpoints. So in this block, we'll say assert equal chords. Let's collect this into a vec. And then chords.length is 2. And then we will return chords. Well, just vec2 new chords 0 chords 1. And oh, we need to parse these though. Dot parse U32 I32 I32 dot expect should parse to I32, and same thing here, parse I32 expect should parse to I32. This is a little bit say x should, y should, and I mean, we could return some other helpful things, but we can cross that bridge if we need to. Okay, so that collects into a list of endpoints, but endpoints aren't enough. We need we then need every point between the endpoints. So let's say endpoints.intoIter. I guess I have to clone this to do what I'm about to do. .zip endpoints. So now we're getting pairs of endpoints, and we're going to say call them P and Q, and say vec2 get points between P and Q, and then we will flatten, and we will collect into a hash map of vec2 and return that. Let's make this a hash map, a hash set. And make this a hash set. Okay, and get points in between doesn't exist, and this guy doesn't know what type it is, but he should be a vec of something. Okay. Good stuff. Now let's just implement get points between, and I'm doing this on vec2 because I think it's likely to be helpful later anyway. But function get points between left self right self returns a vec of self. Oh, and it occurs to me, are there diagonal lines? Your scan traces blah 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 blah. Each point a straight horizontal or vertical line. Okay. Okay, so let's say assert left.x is right.x, or left.y is right.y. And then what to say here? Let direction be right minus left dot signum. So that'll be the vector that points in the direction we need to go. And then we can just say let mute to return be a new vector. say while let me next equal left, while next doesn't equal right. Next plus equals direction. To return push next. And okay, the last time will not equal right, so at the very end of this we need to return dot push right. Return. Okay. 14. Okay, so if we did this right, this should get us all of the points, just a set of the points, which we will then turn into a hash map, which is great. Now, notice we're only putting in when something is rock here, which is fine, I think, because what we're going to do is make our get function, which will take a self and a position and return a material. And what we'll do is match self dot map dot get of v. I guess this can be a reference, doesn't matter tremendously. If it's a none, then we return error. If it's some material, then we return the material. Why is it unhappy with me? Excuse me. Okay. So now we need the drop sand function. At mute self and a starting position. Which, I mean, again, can be a reference if we want to. Doesn't return anything. And what to say about this? Let's just loop. Now, we're going to need a definition of the abyss, which I guess is just that there is no rock at any point below. Which is interesting, actually. So let's add abyss to our material. And in here, we will need to work out where the abyss is. It's an interesting problem, actually. Well, actually, maybe let's not do that. Let's not do that for now. For now, we'll just calculate it. It might be inefficient, but... So... so here, pub function is abyss. or is above abyss, self some position, returns a bool, and whoops. Returns a bool, and how does it work this out? It just says I kind of think we should work this out ahead of time. Kind of think we should work this out ahead of time. So lines to points, we get all of the points. So maybe what we do is we say lines to points, and here we say let map be this, and this is going to be just rock points. This will be rock points dot into iter dot map. This should be dot collect, and this is a vector. No, it's a hash set. And then we need to find the lowest point for each y we care about. We need to find out how low it goes. So what do we want to say there? We want to say like let lowest points be rock points dot clone into iter. Put it into a new hash set. So maybe map p dot y p dot x p, and then we reduce these. So now this is a vector of x's to its points, and we would want to reduce that. Or fold, I guess fold. Something like hash map new and accumulator element accumulator, though this needs to be a tuple, I think. Accumulator dot if accumulator contains element, then accumulator dot push contains.element.0, then push, then basically I'm trying to take all the points. I'm trying to get a map from each x to all of their points. That's not what I care about, though. I actually only care about the minimum. So if it contains element 0, then if element 1 maybe we just keep p.x and p.y around. p.y. So then if accumulator contains it, then we say if element 1 is less than accumulator dot get element 0, unwrap, then accumulator insert element 0, element 1, and otherwise we don't have to do anything about it here. But then here we need to say accumulator.push insert element 0. So the idea collect the end of this. So the idea here, and I've not gotten it quite right, but just make sure I have the idea right, is that we're going to take our rock points, we're going to create a map that's basically the elevations or the heights of each point indexed by the left right of each point, the horizontal distance. Something wrong with my parentheses here. It's okay. Why is this unhappy with me? Close the map. Dot fold. So it takes a single two-tuple as an argument. Oh, is fold not the one I want? Is it reduce? I never remember which one's which. No. Fold. Closure is expected. Oh. So I was just wrong about this. And then mismatched closing delimiter. There we go. Okay. So accumulator is a hash map. No method found for contains. Contains key. There we go. And okay. And P rock points clone. There should be a hash set of points. Which it's not, because we need to flatten. And now, okay, so we get the heights indexed by the horizontal position, and then we accumulate them by saying, look, start with an empty hash map, and then if I've already jammed something into the hash map, check if now my new height is even lower, and if it is, use that instead. Otherwise, jam my XY into the hash map. So we should end up with basically a hash map from horizontal positions to the lowest point that they ever show up. Do I need to collect at the end of this? Don't. Okay. And then what's the issue here? Expected. Consider borrowing here. Let's just define this. Hash map I32 is correct. So if the I32 is less than, so we borrow here. And then the issue is that get returns an option. So I guess we can just borrow here. Okay. And then insert, we need to just at the end of this we need to return the accumulator. Okay, nice. So that gets us the lowest points. And so any point below there, or that doesn't show up in the map, is in the abyss. So let's just put this into the type lowest points. Hash map back to hash map I32 and then map and lowest points. Hash map I32 lowest. And I kind of want to rename map because now it's a little bit confusing. Let's call it materials. Material map. Material map seems good. Material map. And then lowest points. Okay. And so now function is in abyss self and subvector bool, and here we say match self dot lowest points dot get v.x none. Then that would mean that there's nothing on the whole column, so we would say true. Sum y, we would say what? I'm messing up my indents here. That's the lowest y, that is the rock. lowest rock y, and so we want v dot y is less than lowest rock y. And this can be borrowed. Okay. All right, and so now in order to drop the sand, we're gonna loop until the position of the sand is in the abyss. Oh, no, we're not. We're just gonna loop until it's at rest. So can we use while let syntax to good effect here? So like while let some sand position equals self.step. Doesn't really work. What have I done? We can say let mute sand position equals starting position. Clone, and then while sand, while not is at rest, sand position. Something like this. Sand position equals self.step step sand. And then we don't return anything. Is at rest becomes oh, but it might go into the abyss. I guess the question is really, what do I want the step sand to function to do? Step sand, mute self. Some position. And this is just if self dot get v plus negative vec2 of j. So if it's right below, or we look at right below, if this is material air, then we want to update the position of the sand. But maybe we haven't even put the sand in yet. Okay, so maybe that's the thing to do here, is to say that what you get back is a new vec2. And we can make it an option of a vec2. And so here we'll say return sum v. The thing to do is to take this and say let below be this, let below left be below plus minus vec I, and we'll let below right be below plus vec I. And then if self.get at below a normal vector. We're just going to clone it all over the place anyway. Vec_j doesn't exist. Oh, vec2. Then we return below. If self.get below left, then we return below left, and if self.get below right, then we return below right. Otherwise, we return none. And okay, it doesn't like this because it doesn't know how to do minuses, so we can just say this. Yes. Okay. Below is positive. Below is positive. Sick. All right. So, and what's the issue here? Oh, duh. Equals material error. All right. So we check each of the places that it could possibly be, that there could be open space, and if there is, we return. Now the only problem with this is that it can be in the abyss already, and so if it's in the abyss, I think we also want to return none. So we can say if self is in abyss v, then we return none. And we can call this get next sand position. Be a little more explicit. And now I think maybe we can say while let some sand position be it like doesn't quite work. Get next sand position. I think this doesn't quite work because so this shouldn't mutate anything. And then step sand isn't necessary. So we just keep getting the next sand position. Until we run out. And once we once we stop getting the next position, we need to insert. So we need to say self dot material map dot insert sand position. Yeah, this isn't quite gonna work. So I think the reason it's not going to quite work is because we can't insert this sand position. This is going to be a none. I don't even know what the behavior would be here, to be honest. Because, like, this lets some, like, instantiation of sand position is in a totally different, like, it's stomping on this one, and it's not going to be valid the last time through this loop. It's just, even if it were to work, it would still be confusing, and I wouldn't want to have it in here. So I think maybe we just loop, and then what? As we get rid of all this, we can get rid of this, and here we can say sand position is, I guess we match on it. And if it's some position, then we keep it. We don't have to match, actually. We can map it, I guess. So what sand position is or else unwrap or unwrap or sand position. So that's going to say sand position, you're instantiated at the starting position. Then we keep looping until, oh no, we still need to match. We do need to match here. Okay, let's say match self.get next sand position, just saying sand position over and over again. And then if it's some actual position, then we do this. We don't need to unwrap anymore because we know its position. We don't need to do that. And the sand position is V. Otherwise, we break out of the loop. And sand position will still be whatever it was, which should be the thing we care about. It's got to be this. All right. So get next sand position. What's the problem with this? Expected. Oh, it just equals V. Okay. And are we not allowed to break within a match like this? There we go. Okay. Cool. So we will loop through where the sand is. We will try to get its next position. It will return none in the cases where the sand is already in the abyss, or in the case where it can't move, at which point we will break out of the loop and put the sand into the material map. Otherwise, we will keep looping. That seems very reasonable. Okay. So what else is there? Drop sand until abyss and get non-abyss sand. So that's drop sand. Let's say pub function drop sand until abyss. Start position we still need. And then this will just be right, one other thing. Get next stand position. We do need this to be mute. Because if the sand is in the abyss, we need to just return, or we need to not insert it. So maybe what we actually do is we return none there, and in the case where it's not in the abyss, we return v, some v. And then when we're dropping sand, if it's none, so if it's some position, then we say if sand position equals v, then we break, we insert and we break. If it's none, then we just break, because that means we're in the, oh no, first we say self dot has hit abyss. It's true. And has hit abyss will be a boolean, and it will be false no matter what. Okay. And so that allows us to just say while self dot has hit abyss, while not has hit abyss, self dot drop sand starting position. And then last but not least, we're going to need to count the non-abyss sand. It's going to be get non-abyss sand. And what to say about that? For now, let's just do this by saying self.material map dot iter dot filter m equals material sand, and then we will count that. Oh, right. I only care about the values here. And let's call this count, not abyss sand. All right, making progress. So now what's the issue? Sand entry location probably needs to be a reference. Yep. What else? Insert. Can't borrow accumulator as mutable. Is this a thing? That is a thing. Okay. Drop sand at a sand entry location of your choice. Is sand in abyss? Sure. Let's say has sand in abyss. And then we'll call this has sand in abyss. And last but not least, all of these need to be references. Multi-cursor that. Recursor that. Okay. All right, code is compiling. That's a start. Let's see where we are at. Failed, lots of failures. It's fine. Yeah, there are definitely other tests that we should probably write. So, simulate sand, drop, failed. Has sand in abyss is showing up true immediately. Because some V. Okay. So probably we're falsely saying that there is sand in the abyss. Let's write a quick test for that. Computes abyss correctly. We'll take this stuff and we'll say assert that cave dot is in abyss. What to say here? So certainly everything below 494 and everything above 503 should be in the abyss. So we can say back to new 493 0. It really doesn't matter. Should be in the abyss. Likewise 504 should be in the abyss. Likewise, anything bigger than 10 should be in the abyss. So let's say 510. And 5035 is in the abyss. But 509 is not in the abyss, and 5034 is not in the abyss. And let's just say, like, 500 certainly isn't in the abyss, and trying to pick something in the rock. 499 4 is not in the abyss. Okay. Indeed, this does not need to be mutable. Oops. And okay, so I expect this to fail. It does. And what's the problem? Okay, so 5035, computer thinks is not in the abyss, even though it is. Interesting. So lowest rocks, none seems to be working, but lowest rocks, some. The lowest rock Y we should be getting should be 5034. Needs to be greater than, not less than, because the Y is reversed. Because the coordinates go the wrong way. Kind of the wrong way. Okay, computes abyss correctly is still failing. Now the issue is that at 500 we are in the abyss. Okay, so at 500 I would expect get to return something. You know what I think the issue is? I think the issue is that element 1 needs to be greater than this, because Y again goes the wrong way. And let's just throw a comment in here. So still fails. Still failing here. Why is that, I wonder? So when we expect to get something with a higher value of Y, and then we expect that if Y is greater, corresponds to lower. If our y is greater than that y, then that's even lower, and so we return true because we are in the abyss. Interesting. Let's step through in the debugger. Lowest points.get, and we're just getting the immediate none back. So if we look at self, if we look at lowest points, these look like x values. Hang on a second, but they're not contiguous. They should be contiguous. Lowest points, lines to points. Okay, lines to points must not be working right. Let's make sure we've tested points between. There's get points between, and we expect that vec2 get points between of vec2 like 0. 0, not a thing. Whatever. I vec2 I should just be a vector with vec2 I in it. Same with J. So this I certainly expect pass. It does. And then let's say between yeah, 1, 5 and 3, 5. I expect 1, 5, 2, 5, and 3, 5. I don't have equals defined on these. Partial equals defined on these. Can't compare a vec2 with a vector of vec2s. What I'm doing here. Get points between. That's not what I want. What's the issue here? get points between, returns a vector of vectors. Oh, vector of vector 2. Yep. Okay. And then let's just do the same thing, but using the other direction, and let's go backwards this time. So we'll go from 1, 5 to 1. Let's go from 1, 2 to 1, -1. And then this will be 1, 2, 1, 1, 1, 0, and 1, -1. Okay. Cool, passes. Okay, so that's not the issue, probably. So something else is going on. And it feels like it's in here somewhere. So lines to points, splits on the strings, everything parses, and then we take sequential endpoints and we get the points between them. Seems all right. Just a little nicer. And then we take all those points and we construct the lowest points from them. So let's check this out. Let's go ahead and comment this out for a moment. Oh no, it's going to be fine because it's going to be on from strings. And here we are. So rock points is only 7 points. But if I look at the example, it should be many more than 7 points. So, is line to points not working? We split, we parse. We take the endpoints. We zip them. We get the points between. We flatten them. I don't understand. This seems like it should be working. So these are the lines. I would like to know what endpoints is. Nobody gonna tell me what endpoints is? Clone. Is it? Okay, so clone returned this. This should be, this is garbage though. Endpoints. Why is it not letting me see what is in endpoints? Oh. Shoot. That's why. I forgot to skip one in here. This needed to be zip. Do iter. Skip one. So the whole point is to zip up each endpoint with the next endpoint. All right. Now we've got some test passing. Let's get rid of the debugger. And see what we've got. So, all of our tests except our two actual solve problem, 14a and 14b, are passing. 14a is saying, yes, indeed, 24 is the correct solution to the integration test, and so 763 seems to be the solution to the problem. Let's find out if we're right. 763. Boom. Okay. Perfect timing, so I'm going to have to wrap up in a moment. Go ahead and read the next question, because why not? Can have a think about it until tomorrow. So part 2, you realize you misread the scan. There isn't an endless void at the bottom of the scan. There's a floor, and you're standing on it. You don't have time to scan the floor, so assume the floor is an infinite horizontal line with an x-coordinate or with a y-coordinate equal to 2 plus the highest y-coordinate of any point in your scan. Sure. In the example above, the y-coordinate of any point is 9, and so the floor is at 11. This is as if your scan contained one extra rock path, like negative infinity to, yeah, sure. With the added floor, the example now looks like this. Sure. To find somewhere safe to stand, you'll need to simulate falling sand until a unit of sand comes to rest at 500, blocking the source entirely and stopping the flow of sand into the cave. In the example before, the situation looks like this after 93 units come to rest. Using your scan, simulate the falling sand until the source of the sand becomes blocked. How many units of sand come to rest? Oh man, this seems really straightforward, and I want to do it now, but I don't have time. The only thing is, I wonder if it's going to be slow. I feel like our solution is pretty efficient, though. So we should be able to just add another line. Of rock. It's probably the easiest thing to do. So we already know we can get the minimum really easily. So let's make a quick check here. So drop sand starting position. So let's just say if starting, what's it say? If self dot get starting position equals material sand, just return. And let's have an add floor function. And how's the add floor function gonna work? Well, the certainly we can say like get lowest point. And that's just going to be self.lowest points dot iter dot, I guess I can just say let get lowest y. Seems better. Map p dot y dot min dot expect should always have at least one lowest point. Min returns an option. What's the problem? Oh. P.1. And this will just be an I32. And then we can have an add floor. And the add floor should what? You just say like with floor at the beginning. And then we're gonna need to work out the min x and the max x. Okay, well, I don't think this is too tough, but I have a hard stop at 3, so I'm going to end here for today. I'll be back at 1 p.m. Eastern Standard Time tomorrow, and I will see you then. Hope everybody's continuing to have a great holiday season. Take care.